Hello everybody, welcome to your lesson for this evening. What we're going to talk about today are compound inequalities. Now, this word is probably unfamiliar to you, but by the end of this lesson you're going to know exactly what we mean by a compound inequality. Okay, a compound inequality is the result of two simple inequalities that are combined by the words and or. Now, a simple inequality is just something like x is greater than 10, x is less than or equal to 4. Okay, those are simple inequalities. What we've been working with so far are all simple. So now we're going to take two simple inequalities, combine them with the words and or, and we end up with a compound inequality. Okay, another important word that we're going to talk about today is the intersection. Okay, we know what it means for when we talk about an intersection, you should have some idea what that word means. It is a region that shows the numbers that are solutions of two separate inequalities. Okay, we're going to look at an example of that right now, actually. So if I have these two circles here, I have one circle that represents all the solutions to x is less than 10. And then I have another circle that represents all the solutions to x greater than or just greater than 0. And then I have this overlapping portion right in here that is going to contain the solutions to both of those circles. All right, so let's write down some values. Our directions say to write down 3, but we'll maybe write some more. So let's talk about numbers that are just less than 10. Let's go through some. 4 is less than 10. Let's see here. We know that negative 12 is less than 10. Negative 6, 0, 5, 3/4. We could go on and on. Okay? If I talk about values that are greater than 0, 2, 5, 12, 1/2, 15. Okay, any of those numbers are all greater than 0. But then you have this area in the middle that is the overlapping area. So if it makes both x less than 10 and x greater than 0 true, we're going to put it in the middle section. Okay, so let's look at the 4. Okay, 4 is less than 10, but 4 is also greater than 0. So it's going to go in this middle section here, and I'm going to erase the 4 from this circle because it makes both true. Let's look at 5. Is 5 less than 10? Yes. Is 5 greater than 0? Yes. So that would also go in the middle section. Negative 12. Negative 12 is less than 10. Is negative 12 greater than 0? No. So it's where it belongs. 0. Is 0 greater than 0? Nope. So 0 has to be in the left circle. Negative 6 is not greater than 0. 3/4 is greater than 0, so we're going to move it out of this circle, and it actually belongs here. Okay, let's look at 2 in the right circle. 2 is greater than 0, but is it less than 10? Yes, it is. So it's going to go here as well. 5 would go here. 12. Is 12 less than 10? No. So 12 stays where it is. 1/2 is going to move over here. And 15 is not less than 10, so it stays there. Maybe we could add a couple more numbers here, just so they're a little more balanced out. Okay, so that's what it sort of means. You're either less than something, or you're greater than something, or you could be both, and that's when we would use the word and. These numbers here in the middle are less than 10, and they are greater than 0. Okay, so let's look at this slide here. I want you to pause the video and write this down. Okay, so now that you have this in your notes, you see we have and statements and we have or statements. All right, and this little map here shows you kind of the difference between the two. Okay, so it tells you how the two are different when they're written. And statements are written like x is greater than 4 and x is less than 9. Okay, if that's true, we can write it in one compound inequality together, where we have 4 is less than x, which is less than 9. Okay, you see how it is graphed it's shading the area in between the 4 and the 9, all the values that are greater than 4 and all the values that are less than 9. And the solution is all of the values that make both inequalities true. It has to make both inequalities true. Or statements are written separately, whereas and statements we could combine into one inequality, that inequality right there. Or statements have to be written separately. Okay, it's going to satisfy only one of the inequalities, either this inequality or that inequality. It does not satisfy both of them. Okay, both types of compound inequalities are solved, though, as if they were two simple inequalities. Okay, and solutions to both types are shown using a number line. All right, so this will make more sense when we do some examples. If you look at this one, this is an and inequality. Okay, so we're going to graph all the solutions that are less than 10, x less than 10. So as you can see from this top graph here, I've graphed everything less than 10, just as we would have earlier on in this chapter. Okay, we have an open circle because it's strictly less than, and we shaded to the left because we want all values that are less than this 10. Okay, if I graphed the values x greater than 0, I have an open dot on x equal to 0, and I shaded to the right because I want numbers that are greater than that. But because this is an and statement, I want numbers that satisfy both. So that's where these dotted lines come in, right here and right here. They're acting as the boundary for where the two simple inequalities overlap. And where those two inequalities overlap is this area right in here. So that is the solution to this inequality up here, or those two simple inequalities. Okay? Let's look at this. It says the pH level of a popular shampoo is between 6.0 and 6.5. Inclusive. What does inclusive mean? Inclusive means that we're including the 6 and including the 6.5. So if we talk about open and closed dots, we're going to have what kind of dots here? Closed, because we're including those values. So if I use inequality symbols, I have to remember to put that equal to line underneath. Okay, so if I know that my pH level, we're going to call that x, is between 6 and 6.5 inclusive. So x falls, x is going to be greater than 6.0, greater than or equal to, since it's inclusive, and we know that x is smaller than or equal to, less than or equal to, the 6.5. It's somewhere in between there. Now, those are two simple inequalities written separately. I'm going to combine those two together and make one compound inequality. To do that, you always start with the smallest number on the left. We always think of a number line. Smallest number goes on the left up to the biggest number. So I start with my 6.0 on the left. Okay, now your variable always goes in the middle. Variable goes in the middle, and then the largest number, again, think of a number line, goes on the right, 6.5. Okay, now we need to decide our inequality symbols. If I look at this simple inequality right there, I see that x has to be greater than or equal to 6.0. So when I fill in my inequality right here, I have to make sure that the point is pointing at the 6. Or another way to think of it, the mouth is open to the x, so the mouth has to be open to the x when I write it in this compound fashion. Okay, so that's going to be my inequality there, and now I need to fill in my inequality into this spot. Okay, I see from my simple inequality here that x is less than or equal to 6.5. So this one's easy. The point is facing the x, the mouth is facing the 6.5, so I write it like that. So the compound way of writing this, the compound inequality to represent this word problem would be 6.0 is less than or equal to x, which is less than or equal to 6.5. That's taking two simple inequalities, writing them together as one compound. All right, now let's look at an example here of a problem that we are going to solve and then graph the solutions of. This is a compound inequality. This is an and statement, two ands put together here. So I know that I could solve these separately if I wanted to. I could say 8 is less than 3x minus 1, and we know that 3x minus 1 is less than or equal to 11. Both of those are true. Now, I could solve these individually by adding 1 to each side. I get 9 is less than 3x. Now I divide each side by 3, so I get 3 is less than x. If I rewrite that with the variable on the left, I get x is greater than 3. Now, I have to solve the other simple inequality. I get 3x is less than or equal to 12. Divide each side by 3 to get x is less than or equal to 4. So I know that my solution is x greater than 3 and x is less than or equal to 4. So now I need to graph this on a number line. Okay, so I draw my number line. I know that I have 0, 1, 2, 3, 4, 5. I have an open dot at 3 because it's just strictly greater than 3. So an open dot at 3. What kind of a dot do we have at 4? It should be closed in because it's less than or equal to that. So if I have to be greater than 3, that means I shade to the right. But if I have to be less than or equal to 4, I shade to the left. But I don't cross over the dots, I just shade in between. So the solutions to this problem are a very, very small area. It's all the numbers greater than 3, but less than or equal to 4. So some values that would make this true would be x equal to 3 1/4, or x equals 3 1/2, or x equals 4. Those are just a couple possibilities of values that would make this true. There are lots more. Okay, but then there's another thing that I could do in this problem, and that is solve it. Instead of writing it out as two simple inequalities, I could actually just work the problem the way it is written. So if we wanted to, let's see, I'm going to erase this now and show you the other way that I could work this problem. Let's see here. It's going to get the same answer. I'm just going to work it all at one time. Okay, so I could just solve it like this. I could add 1 to each side. And by each side, I have to add 1 3 places now. I have to add it to the left inequality, to the right inequality. And now I have 8 plus 1, which is 9, is less than 3x. Remember that these two things would cancel. My negative 1 and positive 1 is less than or equal to 12. Now your goal is to get x by itself. So now I'm ready to divide each side, both sides of the inequality, by 3. Those 3's cancel, so I get 3 is less than x, which is less than or equal to 4. Now if you remember in your notes, you had that exact same thing written down. So it's just a matter of whether you like to break it up into two simple inequalities or if you like to just work it all at the same time. Now we're going to take a look at OR statements. OR inequalities are different than AND. They only satisfy one inequality instead of satisfying both. So look at this one. I have x is less than 0. I graph that by going to 0 and then graphing everything to the left of 0 with an open dot. If I have x is greater than 10, I'm here at 10, and I have an open dot pointing to the right, shading everything that's bigger than 10. So that is them separately. But then when I put them on one number line, I just write exactly what I just drew in the previous two problems, but just on one number line to represent the values either make this part true or they fit in over here. Is it possible to fit in both? No. I can't be less than 0 and be greater than 10. Can't happen. There are no numbers that satisfy both. So your solution would be one or the other. Okay, let's take a look at an example of that. Notice OR statements, I don't combine into one because they're not making both true. They're only making one true. So I have 8 plus, I'm going to make that an x just so you can tell the difference between the t's and the plus sign. So I have this inequality, or I have 8 plus x is less than 2. I solve these just as if they were two separate simple inequalities. I get x is greater than or equal to 7 minus 8, which is negative 1, or I solve this inequality and I get x is less than -6, 2 minus 8. So now I'm going to graph this on my number line. I have the values -1 and -6. So I have -1, -2, -3, -4, -5, -6, -7. This would be 0. Okay, now I need to decide my open and closed dots here. X is greater than or equal to -1. So I'm going to have a closed dot at -1. And I'm shading everything that's greater than that. So that's going to go to the right, numbers that are greater than or equal to -1. And then I also have an inequality that said x is less than -6. So at -6, I have an open dot because it's exclusive. And I want numbers that are less than that. So I shade to the left. So what that means is in order to satisfy this inequality, you have to be in one of the red regions. Okay, so that implies that this region right in here is not going to be a solution because it's not shaded. Okay, but everything else, all other numbers would be shaded because they'd fall into one of the two red shaded areas. All right, now we're just going to do the reverse of what we have been doing. We've been given two graphs already drawn, and we're going to write the inequality. So just looking at this first one, you should be able to tell whether it's an and or an or. Think about it. If we have only one area shaded, that means it's got to be an and because they're regions that they both had in common. So if I start with this left point here, I have x was what? If they shaded to the right of the -2, that means that x had to be greater than -2, right? And now I need to look at my other point. I look at this point right here, which is 5. X, if I shaded to the left of the 5, that had to be less than. Now it's exclusive because those dots are open, right? So I don't have equal to lines under them. So I have those written separately with an and. But I'm going to combine them into one compound inequality instead of two simple. Remember how we do this, guys. Smallest number on the left, that's our -2. Biggest number on the right, that's our 5. Variable, always in the middle. Now you decide, look at your inequalities and decide which way to write them in the compound inequality. If I look at this one right here, I see that x was greater than -2. So the greater than, the mouth was opening to the x, so it would look like that. If I look at this one right here, the mouth was opening to the 5, so it looks like this. Okay, if you ever get something where the arrows, the inequalities are pointing in opposite directions, like something like this, you would know you've done something wrong. Your arrows are always going to be pointing in the same direction, either less than or equal to. Now let's look at the next one. I see my left value tells me that x had to be, they shaded to the left, so I know that has to mean x was less than -7. It's less than because it's an open circle. Or the values could also be at this 0 here. So x is what? It's a closed-in dot, so I know that is going to have an equal to line underneath it. Is it greater than or less than? Greater than, because they shaded to the right. So greater than or equal to what value? What's our critical point? 0. Can you combine an or statement into one inequality? Nope, you have to leave those separate. All right, that is it. If any of this didn't make sense to you, please rewind the video. This is a really important concept that can be difficult to grasp, but go back, listen to a couple of these examples again, and we'll practice this in class. Have a good night.